Hey everyone, we are the iRisc team. I am Amarnath.
I'm Swati.
I'm Lars.
I'm Vasilis.
I'm James.
I'm Tom.
Our project is part of the E6350 offered by Columbia University, taught by Professor Peter Kinget, co-supervised by Professor Mingo Sia, and sponsored by Apple.
We have built a system on chip based on the open source 32-bit Ibex RISC-V core. Our system integrates 64 kilobytes of on-chip SRAM, communication peripherals such as UART, SPI and GPIOs, and is capable of executing almost any C program.
And now I'm going to show you a brief demonstration of what our chip can do. So just to give you an overview, this is our PCB. You can see our chip here. This is an LCD solely controlled by our chip through SPI. We also have UART on our board. You see two switches, which are direct inputs to the chip via GPIO, as well as 6 LEDs, which are also direct outputs and GPIOs. This is the reset switch, and here we see a piezo element which serves as a speaker powered by our GPIOs. To run a C program on our chip, we compile it with a RISC-V compiler and then load it onto the chip with our scan chain. This process will be described in more detail later on. Now we have programmed our chip with a comprehensive program that showcases all the capabilities of our chip. So let's activate the reset first. We write to the display. Oh, did I do something wrong? Good, just kidding. So this is our menu. We have 3 subprograms. I'm going to start with the first subprogram, which we call print prime. It shows the mathematical capabilities as well as our interface UART. For that, I'm going to connect the UART wires real quick. And on the display, you can now see, as soon as I start the program, you can see with every click the next prime number. And I can do that fairly quickly, and our chip is able for a long time to calculate them in basically real time. It goes through a C program. You can see that in the source code. Now I remove UART and I go back, and now we have play a game. So I'm going to showcase the game now. If we start this game, we see with the 2 buttons I can move our player, which is the X, and we have to avoid touching the coming obstacles. And as soon as we get hit, let's say now, we're game over. So we can also play a game with our chip. This game also showcases the capabilities to write to the display via SPI. Last but not least, we can play Happy Birthday. So if I press both buttons together, we will not only print the lyrics to Happy Birthday, but we will also toggle a GPIO in the correct frequency to play Happy Birthday with our piezo speaker. That was our demonstration. You can keep watching for more detailed description of our chip and all our capabilities.
We are now going to give you first a brief overview and then a very detailed description of this project. You have just seen the demonstration, so next we're going to talk about the block diagram and the system specifications, before we then dive deeper into the system architecture, the design flow with front-end and back-end, pinout and bonding diagram, the software and testing flow, as well as the PCB design and the layout of a PCB. And finally, we conclude our project and say thank you.
So first and foremost, we have the block diagram. In blue are the components that are present on chip, and in gray are the components that are present on the PCB. So in the center of it all is the RISC-V Ibex core in green. On the right of it in orange are the components which are required for the RISC-V Ibex core to function. Our RISC-V Ibex core is the 32 IMC core that is taken by by low risk, and it is an open source core that is available online. It has seen multiple tape outs and has also a well-defined software flow which is the reason why it was chosen. On top of it is the SRAM memory that was built by the ARM artisanal compiler. It is a 64 kilobyte of memory, which has 32 kilobytes of data and 32 kilobytes of instruction memory. On the right here is the scan chain, which is the primary source for taking input from the Arduino and feeding it into the memory, the clock generator, and the FSM. The scan chain has 5 inputs and 1 output, which helps us communicate with the Arduino. The scan chain configures the clock generator, which can take multiple frequencies and can program the core to run slow or fast as required. The FSM is a debug control system which allows us to run the core in multiple modes, such as idle, running for a few clock cycles, or running as much as needed. On the left of the Ibex core are components which are not essential but are added to communicate with the outside world. To add the peripherals such as GPIO, SPI, and UART, we had to add the AHB bus, which is the AMBA AHB bus. The AHB bus is also configured to interact with the data memory, and all of this interaction is done through memory mapped. Hence, the AHB bus also has a decoder in the middle. The GPIOs are configured as 6 outputs and 2 inputs. The outputs talk to the LED network, and the inputs take input from the keys on the PCB as seen in the demo. The GPIO is a very simple register-based GPIO, which for the outputs is registers and for the inputs works as a synchronizer. The AHB bus talks to the SPI and UART through the APB bridge, and the SPI and UART are open source open source pulp peripherals. The SPI talks to the LCD screen and the UART as output to the PC. Now we will talk about the chip specification. The CPU architecture is RISC-V 32IMC. We have on-chip memory of 32 kilobytes of data and 32 kilobytes of instruction. Multiple peripherals such as GPIOs, which are configured as 2 inputs and 6 outputs. UART, which is just output, and SPI, which is also just output on the chip. The programming interface is scan chain, which is 5 inputs and 1 output. The power domains, we have multiple power domains on the chip, including VDD core and VDD test, which are analog power domains, so they can be changed a little bit to check about the power. They're both configured to 1 volt right now. And the VDD IOs, which are digital power domains, which take 2.5 volts and 1 volt power. The maximum frequency that we have tested on the chip is 140 megahertz, which was generated by the clock generator. And the power consumption at 60 megahertz is approximately 40 milliwatt. The die size is 2 mm square and the transistor count is 500,000 transistors. Now I will be talking about the clock generator benchmark. The clock generator has the capability of generating multiple clock frequencies. On the right here, you can see that the clocks go from 9 kilohertz all the way to 1.5 gigahertz. However, for our core, the maximum working frequency is 140 megahertz. And for the peripherals, the working frequency per application is 140 megahertz for the GPIO, but 60 megahertz for the UART and SPI.
Now we will go into the detailed description of our system, the microarchitecture and the architecture of the chip. One of the most important parts of our system is the scan chain, which allows the user to load instructions and data into the on-chip memory before invoking the processor. The scan chain has 2 operations, scanning in and scanning out. Generally, both operations are performed by a single scan cell, although for simplicity in this figure, we separate the 2 operations into different cells. Each scan cell is responsible for 1 bit of the data memory or instruction memory ports, or 1 bit of the clock generator or FSM registers. As you can see, for example, at the right side of the screen, 1 scan cell is connected to the 31st bit of the address of the instruction memory, while On the left, you can see that another scan cell is connected to the first 31st bit of the data of the data memory. The scan chain has 5 inputs and 6 output pins. The scan-in is the actual port that the real data are passed through to be loaded to the scan chain, while the scan-out is connected to the last cell of the scan chain and is used to read out data from the memory. Also, we have the scan-in, out, the load, and the scan chain clock, which will be explained later. I would like to take you over the scanning in process. As you can see here, every scan in cell is connected to one input of the max, while the other input is connected to the core. So, and the output of this max is connected to the IMEM, for example. During scanning in process, this max allows the scan chain to access the memory. In this way, the user is able to write instructions into the memory. While normal operation, this max allows the core to be connected to the memory, and thus the processor is able to fetch the instructions. Let's go over a detailed description of the microarchitecture of our scan chain. The most important part is that for data transmission, we use transparent latches instead of conventional flip-flops. It is known that conventional flip-flops connected back-to-back may lead to hold violations that could be catastrophic for our chip. For these reasons, we use two back-to-back transparent latches, which are clocked by two non-overlapping clocks, phi and phi bar. The scan in-out signal controls the operation of the scan chain, if it's going to be scanning in or scanning out. As you can see at the top, one multiplexer is driven either by the output of the previous scan cell or from the data or instruction memory. When we do scanning in, this multiplexer allows the output of the previous cell to go through, and in this way, we're able to load every scan cell with the appropriate value. During scanning out, the multiplexer allows the data memory or the instruction memory information to be loaded in the scan cells. At the output of each scan cell, we use one register, one conventional flip-flop. This flip-flop, as you can see, is controlled by the load, is clocked by the load signal. During scanning in, once all the data are placed at the output of the transparent latches, we use one pulse of the load signal to load this register. Once this register is loaded, the data are connected, are driving the actual memory address or memory data that we want to write. Also, each scan cell uses two back-to-back inverters to implement a buffer. Here we can see another view of how the scanning in process works. Let's say, for example, that we have the instruction memory on our right. At the bottom, you can see one multiplexer that is driven by the scan chain to IMEM address and the core to IMEM address. This multiplexer is controlled by this signal, which is called scan chain to IMEM control. During normal operation, if the signal is 1, that means that the max allows the core to IMEM address request to drive the instruction memory. In this way, the processor is able to send the address of the IMEM that wants to read. During scanning in, this scan to IMEM control signal is 0, so the address provided by the scan chain is driving the pins of the instruction memory. In this way, we are able to allow accessing to instruction memory and data memory from both the core and the scan chain. Also, as you can see at the top, there is one OR gate that is used to drive the clock pin of the memory. And this OR gate has inputs the scan clock and the system clock. In normal operation, the system clock is driving the OR gate, and then the memory pin of clock is driven by the actual system clock. During scanning in, the system clock is gated, and the clock pin of the memory is driven by the scan chain clock. As explained, to be able to generate fast clocks on chip, we use an on-chip clock generator. This clock generator can be configured during setup through the scan chain to decide what clock period to generate. The most two important parameters are the div and FC parameters. Our clock generator is implemented as a ring oscillator, and the effective length of it is decided by the 6-bit FC parameter. The div 4-bit parameter is used to decide the division value that generates the internal clock. Also, our clock generator provides support for external clock if it's needed for debugging. As you can see, the clock external can drive this multiplexer, which is controlled by the external enable signal. So the selected clock can drive the gating FSM. The HB bus is an essential part of our chip that enables communication of the processor with the data memory, the GPIO, UART, and SPI. The HB bus that we used is compliant with the HB protocol and contains signals like the H reset, H write, H address, and HW data. It also contains the address decoder that is used to generate requests for the specific subordinates, which are the DMEM, the GPIOs, and the HBB to APB bridge. The APB bridge was used to integrate the UART and SPI open source modules that came with an APB interface. The manager of this architecture is the load store unit of our core, and is the one that issues requests for the subordinates. Based on our memory map, the address decoder generates requests for the specific subordinates. The memory map that we used can be seen in this slide. Every component of our chip, like the instruction memory, the data memory, the GPIO, the UART, and the SPI, have a specific predefined start address, length, and end address. On hardware, we use this information when we build the HB bus. On software, we use this information to write to specific registers during configuration before program execution.
So I'm gonna give an introduction for our UART and SPI. UART is Serial Asynchronous Communication Protocol, and our UART is memory mapped. It's required configuration of several internal registers before initiating any data transfer. These registers, such as DLL and DLM, which is divisor register for baud rate configuration, and IER stands for interrupt enable register. LCR is line control register, which is basically for data format configuration like parity start bit, stop bit. The LCR is line status register for TX status reporting. And finally, THR is basically a FIFO that holds the data to be sent. And as you can see on the right, this is our detailed hardware diagram. And on top is our baud generator. And this is TX part, and finally in the end is interrupt block. And we also have an APB interface that enables communication between the UART module and the host system. The SPI is another protocol which is synchronized, so it has a clock. The SPI module has a similar structure, which is like the master controller and FSM, including generating the SPI clock signal. Commands are sent from CPU to the SPI host before transmitting data. And below is several internal registers we need to set. SPI length defines the number of bits for command, address, and data. The length of each of them is set to a byte in our project. And clock divider sets the SPI clock frequency by dividing the system clock. SPI command, SPI address, and TX-FIFO holds all the data for transmission, and which is all basically a FIFO. And finally, register status activates the SPI clock and initiates the data transmission.
Now we will be talking about the IC design flow. The design flow that we have used is very typical to all the digital design flows that generally exist, where we start with the RTL model, generate a gate level netlist, generate a layout, and then finally generate a GDS, which goes to the fabrication. For the RTL model, we have all the RTL files, including the memory file generated by ARM, the Ibex core files that we take from the low risk, the peripheral files that we have taken, and we have created a few files of our own, including the bus. And then we take all of this, we perform first level of behavioral simulation with the software flow that we already had. We take this and then we feed this into the logic synthesis using the tool design compiler. The logic synthesizes our gate level netlist, where we check every parameter of STA and power analysis using prime time. Moreover, from the gate level netlist, we perform another verification, which is the post synthesis verification, again using model sim. After everything passes, we feed this to the Innovus, which is our placement and routing tool, which generates a layout. On the top here in the gate level netlist, we fix all the setup errors, and in the layout here we fix all the hold errors in that we see in the static timing analysis. We also do a power analysis using prime time. The layout files are again finally checked with the post APR verification test bench, and if there are any errors, that are corrected either in the layout steps, in the gate level netlist step, or in the RTL model step. After everything passes in both STA PA analysis and the post APR verification analysis, all the files are fed into Virtuoso, where we do layout verification, LVS and DRC checks, and we integrate the final pads, the IO pads, and then we generate the GDS. Now I'll be talking about the design flow for the front end. These are the design iterations that our project did. At the 0th version, we started with our core, which was a small Ibex core, and had a flip-flop based memory. We took the core and then we verified it with the verification of the software and the tool chain, and we made sure everything worked. After that, we started integrating things to make the SoC. First, we started with integrating the SRAM with the memory wrappers. Then we integrated the bus, scan chain, GPIO, UART. After this, we started integrating the clock generator, pad frame, and IO cells. And then finally, we integrated FSM and increased the memory size to what we have today, which is a 64 kilobyte memory, 32 kilobytes for instruction and 32 kilobytes for data. And finally, we integrated the SPI. This is how we are doing the design iteration, but parallelly, we were also doing all the backend iterations for the same. So I'll be talking about the synthesis modularity in this slide. So all the things that are in blue are synthesized modules, and all the things that are in white are not synthesized. So firstly, we'll focus on the DUT. In the DUT, the Ibex core, AHB bus, and peripherals in the middle are synthesized. The DMEM wrapper is synthesized, but the SRAM is not synthesized because the ARM compiler generates the GDS, and we treat the synthesis of DMEM as the DMEM wrapper plus a black box for the memory. Similarly, for IMEM wrapper, the we only synthesize the wrapper because we already have the GDS file for the SRAM. Outside of it, the test FSM is synthesized, but the scan chain and clock generator are not synthesized. The scan chain and clock generator use standard cells, and hence we do not need to synthesize these modules.
I'll be talking about the backend P&R flow and give an overview of how we turn our gate level netlist into an actual layout. So this is the final layout inside Virtuoso. As we can see, because the memory has a lot of metals and very dense standard cells, Virtuoso is not able to render it properly. So we make this simplified graph to show everyone where our macros are. So we have two main power domains. VDD test includes scan chain, test FSM, and clock generator. VDD core has two memories, instruction memory, data memory, and the core. The memories are placed on the very edge of the DUT because we want a huge area for routing and placing all the standard cells. And the core is slightly shifted upward because we want to keep the clock tree down here. We also added placement blockages around the edge of the data memory and the instruction memory, so their standard cells are not placed on the very narrow, shallow trenches over here and here. The scan chain is a very long strip because it has both connection to the instruction memory and the data memory. As we can see on the real image, there are connection over here, which is make it very easy to connect to everything. So let's move on to the core layout. For the core, we're using metal 1 as a power supply to all the standard cells. We created a power ring using M5 and M6, and we also added MC6 vertical stripe to have better power distribution. The overall density for this module is 72%, and we also added 49 picofarads of decoupling capacitors. As we can see, because the correct placement of all the pins, the routing inside and the placement inside this core is actually pretty even. So next part is where our memory is. We generated memory using ARM Artisan memory compiler, and we created a wrapper for it to be able to add into the read and write logic. So the logic is here at the bottom and the top, and these are perfectly symmetrical because they have the exact same thing for the IMEM and DMEM. The power supply layout is almost exactly the same as the core, because as we can see, they are at a very similar hierarchy, and this will be easier for us to lay out the actual power grid on the higher level. So the overall density for these two modules are around 77%, and we were able to add 300 picofarad decoupling capacitor at the end. Also, IMEM is flipped upside down because the core is actually inside the center between the IMEM and DMEM, and since they are both connections, it's easier to flip them around. And you can see here the connection is just directly towards the core. So let's move on to DUT and the top level. For DUT, we use M5 and M6 to create a power ring. The density is around 73%, and we have 1.35 nanofarads of decoupling capacitors. For the top level, the power supply is using M7 and M8 to create a grid. M7 is vertical, M8 is horizontal. We'll explain that in detail later on. And the overall density is 73%. These are the modules for the FSM and the clock generator. As you can see, they are fairly simpler compared to the other sections. The density for these two are 60% and 68%. And the decoupling capacitance that's added is 1.5 picofarad and 21 femtofarad. As you can see, we are using the same power grid structure as we explained before because we want overall clear power grid structure at the end. So this is the power grid that we created. As we said before, M6 is within each module, and they are vertical power stripes. And then we use M7 and M8 on the top level to create a power grid. M9 is used to connect the chip to the outside ring of the pad.
So this is the final system hierarchy of our Ibex chip. This is an extension of the previous slide about the synthesized modules, where we have more information as we did the place and route. If you see here, the red is the different power domain from the blue, which is a VDD core versus VDD test. The DUT was supplied with the power VDD core, and the scan chain, clock generator, and test FSM were supplied with the VDD test power. Both of them are configured to be 1 volt, but are separate powers and are both analog powers, which can be changed as we want to change the power and current for the chip. On top of, like, all of these come under the Ibex top, on top of which we have added the pad frame, which are the TSMC IO cells, and the bonding pads, which combined make our actual Ibex chip. This is the final pinout of our chip. The things in purple are the IOs, including SPI, UART, GPIOs here and here, the some pins for the scan chain and the clock, and all the pins for the scan chain here. The yellows are the 1 volt supply to the DUT, as seen here in red. The blue are the 1 volt supply to the test, as seen here marked in blue. The 2.5 and 1 volt supplies are the digital supplies to the IO pads, and the green are ground pins. So this is the final bonding diagram of our chip. As you can see, we are using a 64 pin QFN package, and we have 16 pins on each side. However, due to limitations of our bonding pad size and due to other limitations that we had, we were only able to fit 11 pins on this side, and we were only able to bond out 16 pins on this side. The other pins, which are in black, were not connected, and some of the pins on the length side are bonded down to the package ground. So in total, we have 11 pins bonded out here, 16 bonded out on length, 11 here and 16 here, making available 54 pins overall for our chip.
Software and testing flow of our chip, as well as the code of all relevant scripts. However, all the scripts that we are using are also included on our website through a Git repository. I'll first go over the flow as a whole, and then I will show the code snippets. So let's look at this graphic here. We start with a C program which we write. Then, using all relevant header files and libraries, as well as the linker which includes our memory map, we use a RISC-V GNU compiler to generate a VHX instruction file, which I can also show later. For this process, we use a script in courtesy of Professor Mingo Seok, so we are not showing the code here. However, it's a very standard RISC-V compilation process. Once we have the RISC-V compiled instruction file, as well as the VHX data file if we use separate data segments in our code, we have a script that generates a scan chain signal sequence file. So basically this file contains a column for each scan chain pin, which basically corresponds to each cycle in the scan-in process. This file we send through UART to the Arduino, which we configure in a way that this Arduino basically works as a serial to parallel translator. So it receives the UART, it receives the scan chain signal sequence file via UART from the computer, and it translates it to these 5 output pins, 5 or 4 depending how we configure it, and basically sets the bit stream for the scan-in process. We do that while the chip is in the reset state, and then once it's done, it can then do that at a very fairly high frequency. Once that is done, we activate the CPU by deactivating the reset, and the CPU runs. Before I go into the code in detail, I want to show you how we verified RTL before we got the silicon back. So here's a basic example. We had the C program, we compiled it in the same way we did for the testing. We generate the VHX file. However, as we can do that in a test bench, we just flashed the entire memory in a Verilog test bench with this instruction file bit for bit by bit, and then we just deasserted the reset. So the scan-in process was basically just magically flashing the memory correctly. And then we see here, this is a so-called disassembly file. This is a VHX file, which we will see later. This is a disassembly file, and we will see for every instruction what it means. For example, here, load an integer A1 into register A5, which corresponds to this line in the C code, and then we can map these instructions to separate to certain cycles in the actual simulation. And then we see, for example, here we see the same instructions, and then we see, okay, here it stores a 1, here it loads a 1, and then later we will see a 1 plus 2. So that's how we mapped the functionality of the code. So now let's go over to looking at the actual code. So let's now look into the generation of our scanchain sequence file. So this file uses a VHX file, which looks like this. So this is just a list of the instructions. This is the VHX file for our demonstration program. It contains 2,800 instructions. Each is 4 byte, which ends up being around 10 kilobyte. It takes this input file and it writes as an output file this bitstream. This bitstream file is significantly longer, and it contains 4 columns for each output of the scan chain, which we have seen in the scan chain process. So scan, phi bar, load, and scan in. And this is actually significantly longer. So this is about 5 million lines long, which corresponds to 5 million cycles in the scan-in process, because we have to scan in the entire scan chain, load, and repeat this process 2 times for each instruction. And one progressing in the scan chain requires 4 cycles, because we have to toggle the phi and phi bar separately. But now this file works in a way that we have a function refresh combine, which just takes the most recent value of all these values and combines it to a very long string, which is basically our entire scan-in string. The length of the vectors are defined here. And then basically as we go, we read the instruction file. And so for every instruction, we basically put it on the appropriate part, IMEM and address and IMEM write data. And then we write to the bitstream file the appropriate sequences for each column. I will not go through that in detail, as it is a very, very detailed process, but I think with the comments it can be understood fairly easily. And the output file, as explained previously, is this file. Now, once we have this file with the 4 columns corresponding to all 4 input pins, we use this file to send it to the Arduino, which I will explain the setup to in a little bit. So first we set up our serial connection, and then we basically just take every line from this file, and all we do is basically we combine 2 lines, which then is 2 cycles, and we send it to, we actually take 4 lines as 1 integer, so 16 bits, and then we send it through UART to the Arduino. And on the Arduino side then, all we do is we load a simple setup script to the Arduino. All it does is, at first we use DDRD instead of GPIO, which is just a memory mapped way of writing to the GPIOs, which is just much faster than using GPIO write. And we just realized we can scan in much faster using this method. The pins R2 is phi bar, scan in, and load and scan in. And then basically all it does, it waits till there's 32 bytes at the serial buffer, which happens basically immediately because the baud rate is 1 million. And then it goes through each of these 32-bit bytes, and it reads, basically it sets the outputs based on the one half of this byte. So first the lower half and then the upper half, to set the outputs accordingly. And we actually found that the bottleneck of this is that it can't read faster from UART, so it takes about the same time to go through these 32 bytes as it takes to read from UART. So therefore, yeah, we can't go much faster than this right now. Now we'll show you how this looks on the chip. So the first thing is we write a C program and we compile it with RISC-V and we generate the scan chain sequence file.
Once this is completed, we power up our PCB with either batteries or a 5-volt supply. We make sure that our chip is in reset, and then we can connect the Arduino to our scan chain, which I will just do here real quick. The 4 wires here, as well as a common ground, and then we can begin the scanning process. After the scanning is complete, which takes between 10 seconds and 2 minutes, depending on the length of the program, I can remove the scan chain and activate the reset, and the program will start.
As we discussed previously, our chip has a number of communication peripherals, 2 of them being UART and SPI. I will be going over the testing challenges faced while bringing up the UART and SPI functionality as part of the post-silicon validation process. First, the UART functionality. The UART is used to send messages to the local PC terminal. In our case, only the UART TX pin number 22, is being used, and that is configured as an output. The pin is connected to a UART to USB converter. That is, the UART TX pin is connected to a UART to USB converter, and the USB output is used to connect to a PC. A C program is used to set the baud rate of 57,600 for a clock frequency of 58 MHz. In our case, there were 2 challenges faced. We have 2 parameters to fine-tune. One, we had to determine the actual frequency at which the UART module would operate. 2, we were also supposed to set the baud divisor value. The baud divisor value is a very sensitive value, and it must be set precisely in order to ensure successful communication between the host and the device. Even a slight deviation in the baud divisor value, which would lead to a difference in the baud rate at the host and the device side, would lead to the communication to break up or to be unsuccessful. The UART DLL register is being set in this case with the dev write command. We write to the UART DLL register, and this is the value we write. This is used to set the baud divisor value. In the case of UART, it is expected that both the host and the device are at the same baud rate or expect the same baud rate for successful communication. Next, let's move to the SPI functionality. The SPI consists of 4 pins: LCD to SPI, SPI clock, SPI chip select, and SPI to LCD. In our case, again, the SPI functionality is only used as an output. So we only use the pins SPI to LCD, SPI chip select, and SPI clock. The SPI to LCD pin is used to transmit both command and data to the LCD. Here we have 2 parameters to take care of. One, SPI length, that is used to set the length of command, address, and data packets that are going to be transmitted, and this has to follow the hardware definition of the hardware LCD which we are going to use. Second, the clock div or the clock divisor is used to set the frequency of the SPI clock. The dev write commands are used to write to the reg SPI length and the reg clock div respectively. Let's go over some of the details as to how the SPI based LCD was used on chip to print messages onto the LCD display. So in our case, we use the SPI character LCD backpack from Adafruit, and further this backpack has 5 pins. 1, LAT, which is the chip select, DAT being the data, clock being the SPI clock and these two being the PG pins. This backpack is connected to a standard LCD. In our case, we used a 4-row LCD. Now, let us talk about how this LCD display was programmed. To understand the working and basic knowledge about the LCD display, we went through the Hello World SPI program as part of the example code for the Arduino. So as you can see here, there are a few functions already present, such as the begin, which is used to initialize the SPI display, and some print functions which are used to print messages onto the SPI display. Further, there are also some additional functions such as set cursor, set backlight, and so on, which were also implemented. In our case, please note that we have not used Arduino to program the SPI LCD display. Therefore, it was required to go through the header file here, Adafruit liquid crystal.h, to understand the functions which were written in C, and we implemented these functions in our C program, such that we have a standalone SPI functionality without using the Arduino. So this is the open source GitHub we looked up to understand the basic functionality of the Adafruit liquid crystal.h header file. The header file has a bunch of functions defined as part of it. We went through all this code and came up with our own program to program the SPI LCD display. So let us go over the SPI program which we developed. So this is the demo main.c, which consists of all the program functionality that is required for what we used in the demo. So we include the SPI LCD header file first, which has all the dependencies required. So let's go over the SPI LCD header file first. So the SPI LCD header file has a set of functions written here. The SPI write is the core of the entire header file, which is used to write a sequence of command address and data in a particular sequence using the dev write commands. Further, we have the LCD init function that is used to initialize the display, which in this case, a sequence of hex commands are expected by our display to get it initialized. Next, we have the digital write functionality, which is further used as part of writing to the display. The LCD write functionality, which takes in a character and that is used to write onto the display. The LCD print takes in the exact string which we have to write onto the display. The LCD print, as you can see here, calls the LCD write, and the LCD write further calls the digital write. So all these three functions are sort of knit together. Further, we also have the set cursor function, which is used to set the position of the cursor on the SPI LCD display. This function further again uses the LCD write function here, and there's the no display function, which is again using the LCD write function. The no display is used to switch off the display. The display function is used to turn on the display. Further, using the LCD write functionality, no cursor, remove the cursor, cursor to set the cursor, and further some blink functionality to blink the display on and off. All these functions, as you can see, depend solely on the LCD write functionality. This header file was used, and the functions written in them were used to print basic messages onto the SPI display, like hello Apple, this is iRisc, and so on. Further, we also developed a cool game which can be played on the SPI LCD display on our PCB. So the game goes as follows. There is a character player X, and there are obstacles being generated which are flagged as O or which look as O on the LCD display. The objects are spawned in pseudo-random ways, that is, the object is pseudo-randomly spawned onto the rows 0, 2, 3, 1, 2, 3, 0, 1. This is the sequence of rows in which the objects are spawned. And the goal of the game is for the character to avoid these obstacles. Once the obstacle collides onto the character, the game is over. We have two inputs, GPIO inputs, which are used to move the character to the left and to the right. Pressing one of the GPIO input pins, which is through a button, moves the character to the left, while pressing the other button, which is configured onto the GPIO input, moves the character to the right. So this is the basic game functionality we have. We also keep track of the score, that is the number of obstacles that is avoided by the character.
So in this section, I'll be giving an overview for the PCB design. So as you can see here, if we ignore the mounting holes, there are 4 major parts for the PCB. The first part is power supply, which provides the power for the chip. Second part is decoupling capacitor, which cleans up the power for the RISC-V processor. Third part is level shifters, which we since we want a 3.3 volt output, we're shifting the 2.5 input into 3.3 volt output. And the last part is the chip itself and its the peripherals and connections. So if you look at the power supplies, we have 2 modes of powering our chips. One mode is using the battery over here, and the other one is the connectors, which we can provide the 5 volt input and the ground, and we'll be able to power our chips through these 2 pins. These pins over here are just for testing, so we can see all the voltages of each output, and we will know the level shifter will work separately, not the LDO will work separately. So because we have different voltage domains, we need 2.5 volt, 1 volt, and 3.3 volt. So what I did is I chose this variable LDO. So based on the resistor value over here, the actual output of the LDO is going to be different, even though it's all taken to 5 volt input. These values right now are not listed over here, but they are actually double checked on the PCB, so it's actually working pretty well. I also added these 2 LEDs for the 3.3 volt and 2.5 volt just to indicate that the power is on. So yeah, this is the main power supply. As for the decoupling capacitors, for each voltage domain, I would give like a 10 microfarad capacitor, and for each input, I'm giving a 0.1 microfarad capacitor in. So before we talk about level shifter, I'll go through the chip first. We are programming through these scan chains. These scan chains are using 5 volt supply because we are using Arduino to power our chips. So we have to voltage divided to 2.5 volts, so the so that the I/O cells for the chip will not get burnt. So yeah, these are just power inputs. This is a switch for the reset pins. Because when we are testing the chip, we are constantly resetting the chip. It's always going to be low, so we're using a switch instead of a button, so we can actually hold the reset value to 0 instead of like just having a 1 second press. On this side here, these are the outputs for the chip. These are the GPIO, UART, and SPI. GPIO and SPI are just straight outputs. For the GPIO inputs, I actually provide 2 button switches that debounce over here, and they will be able to provide a clean input to the GPIO 7 and GPIO 7. You can also connect those 2 pins with these pins over here, and it will still work perfectly fine. Also, for each GPIO output, I have this LED here just to show the value of the GPIO output. As you can see over here, this is the non 2.5 volt version, this is 3.3 volt version, and this is handled by the level shifter over here. This is actually a bidirectional level shifter. You are choosing the direction using this direction pin over here. If they're tied to ground, GPIO is from B to A, and you need to provide both the voltage level for the input as well as the output. So yeah, this is basically schematics of the PCB, and now we're going to be moving on to the layout. Yeah, so this is the layout of the chip. All the components are the same from the schematics. This area over here is actually where we attach the display. You see all these mounting holes here. They're the same as the location of the mounting holes for the display. So we're actually able to screw some screws and be able to attach the display directly onto the PCB. And because the this display need these pins over here. I added this connector, so we're able to connect the display directly to those pins over here. Like these SPIS pins are supposed to be down here, but I'm able to drag all these signals up here all the way to the to where the display port is going to be. These are where the 0.1 microfarad capacitors are. This is one single LDO structure. As we can see over here, this is a single structure of LDO, and there are 1, 2, 3, 4, 5 of those. For the power supply, what I do is I lay out the power supply first. So because the chip, if you look at the chip pins, the power supply pins are actually pretty spread out. So what I do is I created this ring of power supplies. So it will be easier to connect the chip to the these power rings. So it will be giving a pretty good connection to the to these LDOs. After laying out the power, I added all the peripherals. These are where the scan chain input is. This is the GPIO LEDs. This is level shifter, level shifter, level shifter, level shifter. This is the reset switch. And this is where the input LEDs buttons are. So yeah, this is an overview for the PCB. I hope you guys enjoyed it. Thank you so much.
Thank you for listening to this presentation. We would like to extend our special thanks to Chuan Tung, Moore, Paul, Professor Mingu Sok, Professor Peter Kinget for their valuable guidance and support throughout this course. Thank you.